Hello everyone, I'm Adil Daily. I'm going to talk about the most important part in our experiment, which is the safety and how safe is safe enough. How safe is safe enough is very simple in our experiment, which is when you saw this partition, which is the warning for laser, is don't look directly into the beam, and also wear the protective eyewear, which will be here. Simply, when we're gonna use the glasses, we have to really be careful about it, such as don't scratch it and take care about it, because actually they are very expensive. As what you can see here is the numbers for the how much it's protected. You can just try it, and let's go to do our great experiment. Here you go, and we just simply to put it back again to the box, and thank you.
Hello, my name is Charles Dominguez, and today we will be working with lasers and learning basics of optics. The objective of this experiment is to learn basic optical principles and coherent optics. We will be working with various optical components such as lenses and pinholes, which you can see over here. In this experiment, we will get hands-on experience with the lasers and optical components.
My name is Samir, and today I will be explaining to you how we gonna measure the diameter for the pinhole. So this is a laser source. It is a helium neon laser for 632 nanometers. Then this one is attenuator, so it can attenuate the laser signal. This is the lens. This is your pinhole, which we'll be measuring. It's right here. And this is the collimating lens. So the job of the collimating lens is to sort of broaden the single point laser and produce a circle of beam of light of parallel waves. And right here is your target. The target, we will be measuring the W from the target. This is an attenuator. So as you can see, I'm going from, so this is the brightest, the light is the brightest at this time, as you can see. Now slowly I'll attenuate the light more and more. As you can see, the intensity of the light gradually is decreasing up to a point where it will become minimum, and then it will become the maximum again. So that's going to be right now. So this is maximum attenuation and this is minimum attenuation.
We are going now to calculate the diameter for the pinhole, which is this one. And what we can see here is the formula. What we can find from here is the distance between the target and the lens, which is 380. And then what we can find, which is the W. How we can find the W from the target, we can see here it's 4 millimeter. From there we can calculate the diameter for the pinhole.
As we can see from the calculation, our D, which is the diameter of the pinhole, came out to be 74 nanometers.
Step of this experiment is to measure the index refraction of this prism using the minimum deviation method.
Actually, as you can see here is the light source. As you can see here,
And then here's the manimeters that generate the single wavelengths, and actually we can control the wavelength using this knob, as you can see. Yeah. And then there is some stuff here, so I'm gonna just say how it's used for. The white light source that I use to provide a different wavelengths, only to know that. The spectrometers that are used to select the wavelength, and even the lens that you can see that align the light beam and focus on the frame. So here is the angle scale, and then which is, you can come here, and these three parts you can rotate it as well.
So pretty much you can measure the wavelength of the light, which you're trying to measure the angles. You can measure it through using the CCD, which is over here, which is essentially a camera, which will be displayed through here. So whenever you're rotating the device, you can see the light when it passes through, when it doesn't, so you can measure the exact angle of it.
Hi, this is Amit, and I'm going to demonstrate the experiment of calculation of refractive index of prism using the minimum deviation method. To begin with, let's adjust the wavelength of the light to a particular value, and then try to adjust the telescope so that you can detect the light coming out of the prism with the help of the camera over here, and it gets displayed on the screen over here. You can see there's this, the other end of the screen gets brighter. Now you can note down the value of the angle using the angle scale over here, and then what we have to do is move the telescope away from the original position so that you detect the light ray again on the screen, and when you reach it to that position, the screen gets the light ray gets displayed on the screen again. Make a note of the angle again. As we can see, the angle of deviation is calculated for different wavelengths.